Hello there and welcome back to Science with a Coffee. In our second lesson today, we are going to be covering the atomic theory. In this lesson, I'm going to be making a full detailed lesson as well as a condensed or summary video. If you just need the bullet points, that video is for you. However, in this video, I'm going to go through all the details that led up to the understanding of the atom that we'll be using in these lessons. Things you might want to know before we jump into atomic theory. The first being that atoms are made out of subatomic particles, you might have heard, and these are protons or positive charged particles, electrons that are negatively charged, and also neutrons, and neutrons are the neutral charged particles that make up the atom, and sub is below, and atomic is just talking about the atom, so subatomic is below the atom or smaller than the atom. So if you ever hear someone talking about subatomic particles, it's just things smaller than an atom, or things that make up an atom. So you have electrons, protons, and neutrons. Next, it would be a good idea to know about how opposite charges are attracted to each other and like charges repel. So that's positive and negative charges. So this might have come up when you've been looking at like magnets or static electricity. Now we can jump into the atomic theory. So we're going to go back way back to the ancient Greeks with Leucippus and Democritus. Leucippus, roughly around 400 BC, coined the term atomos, or what that means in ancient Greek is uncuttable. So his idea was that if you took something, like my eraser here, and you cut it into smaller and smaller and smaller pieces, you would get to a point where you couldn't then cut it anymore. So that was kind of the first theory of what an atom was. Then if you fast forward about 2,000 years, you will get to the first kind of model of an atom, or the first kind of physical representation of the atom. And that was from the scientist John Dalton, and this was in the early 1800s. Now, Dalton, what he came up with was known as the Bullards ball model of the atom, aka like a billiard ball or a pool ball. So this is a sphere, and I'll write this for you, sorry for the squeak. So Dalton, he came up with the Bullards ball model, which is just a sphere. Now this sphere, or this Bullards ball, was very small, indestructible, and indivisible, as in it's not made up of anything else, you can't break it down, similar to what Leucippus was saying, but he was the first one to kind of make a physical model, which was basically a sphere. Then along came a guy by the name of Thompson, and this was roughly in the year of 1897. And what he had going for him, unlike Dalton, is Thomson had about 100 more years of scientific advancement. So Thomson was able to use electricity and magnets to kind of play around with atoms a little bit. And what he determined was with these electric and magnetic fields that the atoms would actually change their behavior or move around a little bit. And because of that, he then learned or theorized that atoms must be made out of things that are charged, or things that have a charge to them. If they didn't have a charge, they wouldn't have then changed in the presence of a magnet or electricity. So what Thompson came up with was something that is known as the Plum pudding. And I'll write that as well here. So Plum pudding. So the Plum pudding model had something that was negatively charged floating around inside a pudding that was positively charged. So the Plum pudding model that Thompson came up with, he knew that inside this atom, unlike what Dalton knew, that we have some charged things. Now, he found out that there was positively charged things and negatively charged things. And he thought they were all together in kind of this like puddingy thing that was moving around. And the best analogy he came up with was something like a plum pudding. So the pieces of plum were the negative electrons, and then the pudding itself was positive. Now, this was a great idea. It was a big step forward, big leap forward in understanding the atom from what Dalton had, and we're now with the plum pudding. After the plum pudding, we then had a scientist and his team, rather, and his name was Ernest Rutherford. Now, Rutherford did a very, very, very famous experiment. So what Rutherford and his team came up with was a more in-depth understanding of the atom. So what they did was they took a piece of lead, which is the atomic symbol is Pb. Now this lead was radioactive. So what that means is these atoms were slowly breaking apart into small chunks of smaller pieces of atom. And one of those particles that you need to know is an alpha particle. So this radioactive lead was shooting out alpha particles, or it was a source of alpha particles. Now, what you need to know about alpha particles is that they're very positive, they're moving really, really fast, and they are also quite small. So they knew all of this at that time. And what they did was they shot these basically really small subatomic particles at gold. So they had a detector, which I will draw as this kind of looking giant Pac-Man-y thing, and they had a sheet of gold. So this here is gold, and the atomic symbol for gold is Au. So we have some radioactive lead and we have some gold. Now this source of lead shot alpha particles. So again, very fast, very small moving, very positively charged particles at gold. Now, with gold, it is very, very malleable. So what malleable means is you can roll it out into a very, very thin sheet, just like the aluminum in lesson 1. Just like this. So picture this, but it's gold. And that is known as gold leaf. So you sometimes might have seen in like places like Europe, gold leaf covering different statues and things like that. So you can take gold, roll it out really, 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 really thin, and then what that does is it's only a few atoms depth or width. So they knew this, and they were shooting these alpha particles at the gold, and they thought if it was like what Thompson believed or theorized, that most of these things should just go straight through, because it would just go straight through all these atoms. However, that was not the case. So what Rutherford and his team found out was that yes, most of these alpha particles flew through and ended up hitting this detector, so that way they can see them just like an X-ray basically. However, some got deflected. So they had spots that came up kind of all over. Now this was puzzling, but not as puzzling as some of those alpha particles, or bullets, bounced back away from the gold back towards them. This detector strip actually went back further, elongate it here for you, and it bounced back and hit the detector. Now what this did is it really kind of took away the idea that Thomson came up with, because what we learned here was 3 main things from the alpha particles going straight through, the alpha particles deflecting a little, and the alpha particles getting fully deflected back at or towards the scientists or the lead. So what Rutherford came up with was something known as the Planetary Model, And this had the nucleus. I'm just going to draw it kind of like some grapes. And the electrons orbiting, hence planetary model, around that center of the atom. Now, this diagram to this diagram, pretty big change. The difference is that all the positive area is in the center of the atom. The electrons, and the shorthand for electrons is E minus to the exponent of. What he found out with these three things is that most of the alpha particles flew straight through the atoms. So if I drew a box around this atom, most of this atom here is empty space. So those alpha particles, if it was flying straight down, it would fly straight through this area. It wouldn't hit anything. So we knew that most of the atom was empty space, basically. Then, when the alpha particles deflected, like these arrows here, we knew that there was something in the atom that was also very, very positive. This is because if you take a very, very fast-moving particle that's positively charged and it comes near another particle that is also positively charged, it will be repelled, or it will push away from it. So what happened was the alpha particle came close to the center of the atom. Let's say it was the lid. It came close and then it got deflected. So that way we know that the center of the atom, or the nucleus, is very, very, very positive. The third and final thing we found from this experiment, or the gold foil experiment as it's typically known, is that when the alpha particles bounced back away from the gold, that not only was the center very positive, it was also very, very, very dense. This is because if you're shooting subatomic particles almost at the speed of light at a very, very thin sheet of gold, and then some of them bounce back at you, it would almost be shooting a cannon at like a piece of paper and having a cannonball bounce back at you. So this was super, super, super puzzling and was not at all what they thought was going to happen. And what that meant is that when the alpha particle came and hit this center, this very, very positive and very, very densely packed area of the atom, it bounced back. So we then have these three things that happened with the alpha particles that led to three changes of the atom. First, as a review, the electrons cannot be inside the nucleus because the nucleus is very, 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 very positive. Then the positive area is located in the center, and it is also very, very, very dense. So that positive charge has to be together. The negative charge can no longer be in there, so Rutherford just said they're on the outside somewhere. So the electrons are on the outside, the protons are in the middle. Very, very densely packed, and most of the atom, as you can see, is empty space. After this was done, we have a few other discoveries that happened. This model, this planetary model, if you watch the popular show Big Bang Theory, this is usually what's flying around in their transitions. So that is the planetary model. After this happened, I'm just going to slide over here a little bit, you get Niels Bohr. Now, Niels Bohr came up with a few different things. Now, he looked at the atom in a slightly different way than how Rutherford was looking. Rutherford kind of helped tweak and understand the nucleus. He had no idea what the electrons were really doing. Now, one of the things that they looked at with this new idea that Bohr had was if you have the center of the atom and you have electrons spinning around it, these electrons are negatively charged, as we've said, and the protons are positively charged. So one of the issues that people had with the planetary model at the time was that those electrons technically should fly into the center of the atom. Like, what's stopping the electrons from just spinning inwards? Because as I said, one's negative, one's positive, and they attract each other. So Bohr tried to look at more so the electrons. That's what he was studying. And he also was using some of the advancements in the field of quantum physics. So this gets very, very complicated really fast. So I'm going to keep this as basic as possible to understand what Bohr was doing. So what Bohr did is he looked at hydrogen mostly, so the gas. And what he found is that when you take an atom, specifically hydrogen, and you give it energy, so you basically electrocute the gas, what happens is the electron will jump up specific areas. And he saw this with it absorbing light, and then when you stop electrocuting it with that light or energizing it, those electrons will come back down to a more stable area, and when they come back down, they move at these specific areas, and when they move up, they move in those specific areas as well. So if you have the nucleus of hydrogen, so I'll just write a little h right there. So this is the nucleus or the center of hydrogen. If you have one electron right here, if you excite that electron, what he found is it will jump right up there. Then, if you excite it even more, it will bounce up to a different area. Now, the electron, he found, was not jumping between these areas. So there's only one spot for this electron to go as it gets more and more excited. So what this allowed Bohr to understand is that there are specific areas or specific seats that these electrons can go to. And how this helped Rutherford is that these electrons, they can move down these different energy levels. However, they're usually happy to stay in the ones that are closest towards the nucleus, and to then move towards the nucleus, it would have to release a lot of energy. So this helped explain why the electrons wouldn't come crashing into the nucleus, and also helped explain where the electrons roughly were in the atom. So Bohr came up with a kind of tweak to Rutherford's idea. So we still have the nucleus, and that nucleus now we know is slightly different, but I'll go into that in a moment. And we have the electrons in these kind of energy levels or shells or orbits. And those will get more complicated as time goes on as well. So instead of just having a nucleus that's positive with the electrons all kind of willy-nilly flying around it, we now have more of an organized understanding of the electrons from Bohr. With Bohr and his model, one difference between Rutherford and Bohr was that Bohr came along and we also added some knowledge from a guy called Chadwick. Now, Chadwick also added some more stuff in there, and what he added and what he did is he used more understanding of how atoms behaved when they kind of exploded. So back then they were still blowing up the center of an atom and things would go flying out. And when those things would go flying out, he found that some of the pieces of the atom, or the subatomic particles, can not only be explained by positive things that we knew about, or the negative things of the electrons. So what he discovered, what he kind of added to this mix, was neutrons. And neutrons have mass, so they weigh something, and they're neutral. So he kind of found with blowing up atoms, basically, that A, they definitely were not indestructible, and B, that some of that mass of the atom has to have a neutral charge. Now, he used things called cathode tubes, and they just are basically electrocuting and blowing up stuff. And so Chadwick found neutrons. Now, these neutrons helped us kind of understand what we know the atoms to be. So we have Dalton, which had the billiards ball model. We have Thompson, and he came up with the plum pudding. We have Rutherford, he came up with the planetary model from the gold foil experiment, where he shot alpha particles at gold foil to find out if Thomson was actually right. And then Bohr, who looked at the behavior of electrons in hydrogen to understand more of the quantum mechanical understanding of the atom, whereas the electrons will only move to discrete or specific areas of the atom. Another way to think of this is how people get on school buses or just buses in general. You have specific seats you go to. No one will sit in the aisle and no one sits in between the seats. You have specific areas you can sit. Electrons, ref of the same idea. So he changed the planetary model because obviously with the planetary model the electrons would spin into the center, and he understood that electrons will roughly stay where they are if they don't release a bunch of energy. So the electrons need energy to move one way and have to release that energy to move back down. Then we have Chadwick, and he came up with neutrons, or found neutrons rather. Now all this information we can put together to make the Bohr-Rutherford model of the atom. So if I just do some magic stuff and snap my fingers, and there you have it, the Bohr-Rutherford diagram of the atom. So this model takes into consideration everything till about 1935. Now, you're probably thinking to yourself, hopefully, 1935 was a long time ago, getting up to 100 years ago. And you're right. This model of the atom is old, but it's very, very useful in understanding kind of that foundational chemistry that we'll be going into, and therefore is very, very important to know. Now, atoms are much more complicated than this. They behave way more not like you would want them to. But in order to get there, you kind of have to first understand how we knew the atom to be before we got all basically quantum mechanic-y. So this model of the atom is, or diagram, is known as the Bohr-Rutherford model. I'll abbreviate that to BR. And the Bohr-Rutherford model encompasses the understanding of the nucleus, which is here, which has the neutrons and protons in the center. You denote the number of protons or the number of neutrons with the number, and then you draw your electrons here. You can draw them as dots. You can also draw them as like X's. It really doesn't matter. And I'll be doing both, as you will see in future videos. So this is the Bohr-Rutherford diagram for carbon. Now, in the next video, I'll go over drawing Bohr-Rutherford diagrams, and I'll be giving us the information we need to draw the atoms. However, that information you get from the periodic table. Before we jump into the periodic table, because that is a quantum leap in itself, I'm just going to give us the information that you would get from it to draw these, and I'll go through how to draw these and kind of the conventions, if you will, of Bohr-Rutherford diagrams. And then we'll jump into the periodic table. And I'll end lesson 2 on the atomic theory here. That's a lot of information, I know, if you want to review it, or if you just want the key points again, I have a summary video for lesson 2 as well. As promised for my videos, I'll end it with the 3 things. First being the tip, which is sleep. Sleep is very, very important. Keeps your brain working the way you want it to. Helps you remember things, stops you from being as irritable and cranky, which is always a good thing, and helps also with your focus in the classroom. So if you're not getting enough sleep, you won't remember things as well, you'll be irritable, and you won't be as focused and learn as well in school. So always, always, always get enough sleep. Roughly 8 hours should do the trick. Then the photo I will post here is a photo I took in Namibia. This is the Milky Way. So this is what the sky looks like when you have pretty much no light pollution. And then the band this week is one of my favorites, and that is Alt-J. Definitely check them out. And with that, I will end it here. So please, if you like this video, give it a big thumbs up, subscribe, hit the bell, and as always, be the ball.